All right, so yesterday we almost finished section 1.4, so we're going to kind of talk about that really quick. And then we'll go into section 1.5, okay? So we did the intermediate value theorem yesterday. We talked about what it looked like in terms of a picture and how we can find certain values within certain y values, our f of a and f of b, as long as the function was continuous within a closed interval, right? So we were able to figure that out. I was able to show you that, and I told you the most practical use of this is to show that there's a zero. So let me give you an example of like the most practical use that you will have for this theorem. Okay, so here we go. So this is an example number. I don't even know what we left off on. Let's find out. Example 5. So does the following function have a zero? Now remember, guys, whenever they say the word zero, what that actually means is, does it cross the x-axis, okay? Whenever they say, does it have a zero, they're asking you, does it cross the x-axis? So does it have a zero between the closed interval from 0 to 2 for f of x equal to x squared minus 2. Now we know that this function has two zeros, right? I mean, you guys should be able to look at the function x squared minus 2 and say, okay, parabola, the minus 2 means it goes under, so it has two x-intercepts. Okay, one on the left side of the y-axis, one on the right side of the y-axis. So you should know that just off the top of your head. Like, you should be familiar with those types of graphs. Okay, but how can I prove that it does have a zero between 0 to 2, right? Well, first off, I know this is a quadratic function, and quadratic functions are always continuous, right? So I know that this function is continuous. Let me make a point of that. Number one, f of x is continuous everywhere. Okay? Quadratic function is continuous everywhere, okay? So we have continuity. So now I just want to check f of a and f of b. In my case, a is 0 and b is 2. So part 2, let's call it part a for part 2, f of 0, and then we'll find f of 2. Now if I can prove that these two things are the same value, okay, then I can try to see if I'm not the same value. If I can show that one of these is positive and one of them is negative. I was thinking of Rolle's theorem. I apologize. You guys don't know what that is yet. But if I can show that these things have values that are positive and then the other one negative, then I know that they have to cross through the x-axis, because that's the only way you can get from a negative y value to a positive y value, or vice versa, positive y value to negative. So let's see. F of 0, that's 0 squared minus 2, which is negative 2. F of 2, that's 2 squared minus 2, which is 2. Right? So if I were just to think about this, I have one point at 0, negative 2, and one point at 2, 2. Now remember, this graph is continuous. There are no holes, no gaps, nothing like that, right? So I have to be able to connect these things, right? In order for those 2 points, is it going to cross the x-axis? In order for those 2 points to connect, is it going to cross the x-axis? Yes. How many times? Well, from 0 to 2, just once. But to be even more specific, at least once, right? Remember the intermediate value theorem says that it's going to occur at least one time, right? At least one time. So we know that this is a parabola, so we know it's only going to happen one time, right? By the way, this was part B, I'm sorry. We know it was going to happen one time. It's going to be right there. Okay? So does the following function have a 0 between 0 to 2? Yes, it does. Right? So I'm just going to put right here. Yes, it has a 0 within 0 to 2. And that's because of the intermediate value theorem. And actually, I should mention it. Anytime you use the IVT, you got to mention it. So, by use of the IVT. So the intermediate value theorem helps me to guarantee that there is going to be a 0 right there. Any questions on this one? So I will give you guys the homework. You know what? Let me pause this and then let me put the homework for you guys. But give me a second. All right. So let's go ahead and continue with the new lesson here, section 1.5, infinite limits. Okay. Now, let me write down the definition of this. So infinite limits. It's a pretty basic definition, nothing groundbreaking, but it does help you understand what we're going to be doing. This is limits that increase or decrease without bound in other words, no restriction as x approaches c. Okay, so let me show you an example of this. So go ahead and keep writing that down. Right now we'll do an example. But infinite limits are limits that increase or decrease without bound as x approaches c. So as you approach your destination, all of a sudden you notice, the value of y is just getting insanely large or insanely small, right? It's either going up towards infinity or down towards negative infinity, right? So here we go. Find the limit as x approaches negative 1 of 1 over x plus 1. Now, you guys probably should know what this graph looks like, right? It's just an inverse function that's actually shifted one time to the, or you're going to negative 1, so one time to the left. Okay? So let's kind of draw this out. So it would be about here. So negative 1 would be an asymptote. The horizontal asymptote would be at 0. So just to kind of draw this out. Okay, there's your graph. There's a sketch, of course, right? So what is my limit as x approaches -1 from the left side of 1 over x plus 1? And what is my limit as x approaches -1 from the right of 1 over x plus 1? So as we approach -1 from the left, where is that going? Negative infinity, right? That's going towards negative infinity. Right? That's an infinite limit. Right? Negative infinity. What if I approach from the right side and get close to -1? Where's that going? That's positive infinity. Right? Does a limit exist? I mean, do the left and right hand limits even have a chance of being the same? No, right? So a limit does not exist. Okay? Even if they were both the same value, infinity, you would still say it doesn't exist, because the limit by definition needs to be a constant value, like a pi or I guess pi is constant, even though it's ever changing. It's kind of weird, but like a 7 or a -1/2 or something like that. That's what you want your limits to be, an actual number. If your limit ever comes out to infinity, you could put does not exist, because there's no way for you to capture a number from that. It's just insanely large. Okay, so right here we're just going to say the limit as x approaches -1 of 1 over x plus 1 does not exist. Okay, that's kind of like the idea of infinite limits. Okay, now there's a part in this lesson that wants me to show you vertical asymptotes, but does anybody here not know how to figure out a vertical asymptote? Because I usually skip that part. I'll show you an example. If you have a function that looks like this, let's make it an 8, just to make sure. Or maybe a function that looks like this. What's the vertical asymptote for f of x? -8, right? The vertical asymptotes are found in the denominator, right? These are numbers that you cannot have, you can't use them in your function, or else it just kind of blows itself up, right? So x cannot be -8, right? So that's our vertical asymptote. X equal to -8 is our vertical asymptote. That's where you draw the vertical line and say, okay, this graph can never be that number. Okay? Actually, I just realized I messed up on the bottom one here. This should be x squared plus 4x plus 4. Okay? So for this other one, to find the vertical asymptote, just factor the bottom, right? So the bottom here, we got x squared plus 4x plus 4. You get x plus 2 times x plus 2. Right? So that means x can't be -2. Right? So x cannot be equal to -2. That means your vertical asymptote occurs at -2. This has nothing to do with calculus. Okay, what I'm doing right now, this is all algebra 1. Okay, so this isn't like crazy calculus magic that I'm using. Like it's just algebra 1. That's all we're doing. Okay, so they want me to go through all this lesson of how to find a vertical asymptote using all these different techniques, and I'm like, why learn a new technique when the original technique is so efficient? Right? It's not hard to do. Just set the denominator equal to 0, solve, and whatever you get, those are vertical asymptotes. Okay? So very important you guys know that. Aside from that, do you guys have any questions so far? No? Well, then we're done. That's section 1.5. Because I'm not going to teach you any crazy techniques for vert asymptotes. Why? It's easy. So I don't have to show you crazy calc stuff for that. So we'll stop right there, and I'll give you the homework.